We see your screen now.
I don't know, maybe because I'm not the organizer. I cannot. I'm trying to. Okay, now I see.
We see you as well.
And you see the screen. This is more
yes,
important.
Yes, the screen as well.
You see. By the way, what do you see in the screen?
The trefoil and the connected sound of two notes. And now the exercise sheet.
Rafael, do you see your picture or just?
Yes, I see my picture.
And okay, when I switch, you see both, right?
Yes.
Now you see Now you say I want to make that you can see the statement of the exercises as well as your picture, right?
Yes. Maybe you can take my picture a bit more on the right then. You take the windows more on the right.
Yes, I'm trying.
Okay.
I'm trying to do this, sorry. Do you see now both?
Yes.
It's not.
Yes.
Very good. Very good. So I just, I was asked that it is necessary to tell that it is recording. Okay.
Oh, okay.
Very good. So I'm very glad to see you. If I can tell this. So we start with the first exercise. So this is, I think this is correct. You are just identified very well. This is the right hand trefoil, right? Right hand.
Yes, right hand. Yes.
The small one that you colored in green. This is the right hand.
No.
No.
No, in green it's the eight notes.
No.
No.
No. In green, you mean?
In green, yes.
You can easily calculate. Can I make it bigger? Too big. It's okay?
Yes.
But it is 1, 2, 3. Only 3 crossings.
Yes. Yes, indeed.
Only 3 crossings, right?
Yes, indeed. Yes.
So
yes.
This is a sum of 2 trefoils.
Mm-hmm.
This is sum of 2 trefoils.
Yes, sum of 2 trefoils.
Yes, and as far as I understand, that this is the right hand and this is the left hand, right? No, both of them are right hand. Natalia, what do you think?
I think we take one right hand and one mirror.
Yes, one.
And some
Yes, this is the right hand. The small one, the green, is right hand. And this one is left hand, because in right hand, this should go up. I'm always have problems, but I think if
in my picture I have 2 trefoils and one is a mirror of
yes.
another.
Can you show your picture?
I can
what should I What should I do?
in my textbook. Sorry.
What should I do? Stop the screen or something?
Can you see my picture in my video?
Yes, I'm trying to make it bigger, but I don't know how to do this.
Sorry, that's all. Okay, this and this. Two threefold.
One is the
This
mirror image of the other.
point, this 2 point cut in this point and glue together.
Very good. So in this picture, we should fix. This is the big one, right? This is the big one.
Yeah, I made a mistake. I connected
Right.
with the. I connected with the 8.
Yeah, and this. Sure.
Yeah, I made a mistake on the right one.
Yes, we need to place the mirror image of this, and this will be the square, right? The square knot is the connected sum of two trefoils of different realities, I don't know, parity, okay?
Yes, yes.
So very good. Very good. Then we should look at the next picture. The next picture I'll try to show. I'll try to show another picture that how to do this that Raphael sent us. Okay. This one. Look. This is a small one, and this is the big one. So both of them are the same. And this is what sometimes, you are absolutely right, that it is the knot which has the number 5-2. But it also, as for me, I'm accustomed to consider it as a generalized knot in the generalized of the figure 8 knot. If we consider figure 8 knot, then there will be 4 crossing. 1, 2, 3, 4. So it will be in this part, it will be 1 crossing less. Okay. And but anyway, it's the next with 5 crossing, so it's almost the same as 4-1, the figure 8 knot, but we have 2 crossings here. There are maybe the canonical pictures, they differ. Either they make this one in the first sheet of notes that I sent you, that was in the lecture. If I remember the second one, maybe it is in this form, but sometimes it is in a little bit different form. This is also the knot 2. And this is okay. This is okay because if we, okay, Natalia, I'm listening. I'm listening to you.
No.
Okay. So the only thing I wanted to tell that if you just make isotopy this loop over here, then you'll have the same as before, only you need to rotate. So this loop is over here, and if we now place this loop here, it will be on the right hand side, and here it is at the left hand side. Okay, so dear friends, are there questions, remarks? Okay, if no questions or remarks, we just identify that this is 2 copies of 5.2. Then the right-handed trefoil or left-handed, it's the same. We should look at the moves. Okay, so we shall look. This is very simple. The first one. Do you see?
Yes.
So this is simple. How to make isotopy? This is simple. You simply make a rotation, and so if you want that, you make the whole space. You rotate, and you get the necessary thing. And this is, I saw that you did, but as for me, it's always not too simple to make it by Reitermeister moves. So I'm very happy that you made this. So Raphael, can you see, because you are the author of this beautiful Reitermeister?
Yes, I can see.
Yes, please.
So first, so we start on the top left. So we take what it's in blue and we push it to the left. So we will get some second.
Sorry, excuse me. The essential is maybe you're right that at first to the left, but essential that you apply, as we did several times, the third, troisième Reitermeister.
Third and
this,
second.
Yeah.
Yes, it's a mix of them.
Yes.
Then what we got a loop that we just cancel with the first Reitermeister move. On the top picture on the right, then we go on the second row on the left. So maybe I should have right as well, that there is also some, I mean, here it's a mix between 3 of them, the 3 Reitermeister moves, because we will have a crossing at some point, so we need to use the third one. Then we will have the second one, it will give us a loop, so we need to use the first one as well.
Right.
So I forgot to write R3 in this one. Then we just, so yes, then we take again what is in blue on the left, and we just push it to the right. So here it's a simple Reitermeister move number 2. Then on the last row on the left, so again so there is a third Reitermeister move, and at some point I guess we will also have a second one to use for sure. And then actually after that we arrive at the last picture, and we just need to use the first Reitermeister move, and then we need just to adjust a bit by pulling a bit the rope, and we get the trefoil with the, or orientation inverse.
Yes, very good. Natalia, do you want to add something?
I haven't done all my homework. I think that's right.
Yeah, no problem. I tried to show what I was preparing when I was thinking about this exercise. So actually this is the same, only this is the left hand trefoil, right? This is exactly the same, what maybe not exactly, but I see that this is the same what Raphael prepared, right? The same way we were going in his pictures. We were going from the right to left, and here we are going from the left to right. So first of all, we make this essential move here is this Reitermeister. So we were going here. At first, if you want, you can create a loop here, and then it was here, and then you can apply the Reitermeister 3. Then you kill this loop as it does not useful now, and then again you are going from, you have this, but you can move through this one, and then again. So here actually this not shown in detail, because here you are making the you're making the Reitermeister here, the first one, or no, the second one, and then the third one to put it here. Okay, then you are working with this loop. It here, then here, then you are dealing with this stuff. This stuff becomes here, and sorry. No, it disappeared. I don't know why. Ah, okay. So I should be careful. And then, okay, several moves, and we are arrived in actually, this is, you see that the rotation, but this is the simple rotation which is done before. When you are using Reitermeister move, you should cross all the things. So if you see rotation, then actually you are crossing. Okay. So does somebody want to add to this exercise? No? Very good. Then we can start the next topic do you see the title of the lecture?
Yes.
Yes.
Okay. You see in good shape?
Yes, yes, all is good.
Very good. So today we shall speak about the prime decomposition. So as we now can add the nodes, we considered them the sum or composition or connected sum, the product, even the word I used. So then the natural question arises that if you have a node, is it a composition of other nodes, simpler nodes? And that's why we arrive to the following natural definition. A node is called composite if there exist non-trivial nodes K1, K2, such that K is equal to the connected sum, the product of K1 plus K2. So this is quite natural definition. And of course, the node is called prime if it is, of course, not a node, but maybe it depends on you. If you consider the number one as prime, okay, then the trivial node is prime. But the usual convention is that the node is prime if it is not one and it is not equal or equivalent as nodes to the composition of two non-trivial nodes. So then, of course, you can formalize this in such a way that if you have a composition, then necessarily you must have either K1 or K2 trivial. We see that trivial, the composition with trivial node is just the same. So please have in mind that this analogy with the prime numbers will become more and more exact. At this moment, it is just an analogy that you have the commutative law of composition, and you try to understand whether you can decompose your objects for the primes, the same as the product of positive integers. Okay. Okay. So to study and to prove the main theorem that we would like to prove today is to prove the following theorem. The theorem that the genus of nodes is an additive function. So this is the if you want to say that this is a homomorphism from the additive monoid of nodes to the additive, not multiplicative, additive monoid of integers. So we shall you should remember the definition of genus. So Natalia, do you remember how you were making the Seifert surfaces?
Yes.
Very good. Very good. This is essential. We need your knowledge about Seifert surfaces. So this is the game that we shall play now. So this will be essential. Of course, it's interesting theorem by itself, but it will be the essential tool for proving the prime decomposition of knot. But to be precise and to work not at the intuitive level, we should have today to work in a little bit algebraic topology. Algebraic topology gives algebraic or sometimes integer invariants, but very often they lead to algebraic invariants. So let us consider the polyhedron, the finite polyhedron that we started maybe at the first lecture. So the invariant of polyhedron that we need is the Euler characteristic. Did you meet Raphael before this notion?
Yes, of course, I did.
Very good. Natalia, did you meet?
Yes.
Very good. So then, but anyway, I'll, as if I prepare, so I'll try to have this, but maybe to remind you, it will be okay. So this is in this manner that Euler was considering it actually for the convex polyhedra. So you take the number of vertices, the zero-dimensional faces minus number of edges, the one-dimensional, then the number of faces of dimension 2, and so on. So as the polyhedron is finite, then the sum will be finite, and it works that for every polyhedron we have this integer, but it is really integer, not always positive, and we'll see that this is essential because there might be many faces of negative of even dimensions, and they may have the negative impact for the Euler characteristic. Okay, so the wonderful fact of the algebraic topology is that the Euler characteristic is homotopy invariant. We shall speak a lot today about homotopy, so I don't, maybe when we'll think about fundamental group, maybe I remind, but this is almost the same that isotopy, which we are considering, but there are no restrictions about one-to-one mapping. It is just a continuous deformation in the most general sense. So the fact from algebraic topology that we need is that the Euler characteristic is homotopy invariant of a polyhedron. So why? So for us, for today and the future, the only this stuff that as a statement is necessary in our work, and that's all. But for those who knew something about homology, I remind why it is so. So for the experts in the subject, I can tell that another way to define, and this will be the same exactly each time. It will be exactly the same number, and it can be expressed by the formula that it is the sum, the same as before, but only you are counting not the number of cells, but the Betti number. This is the rank of the homology group of the polyhedron, and homology is the homotopy invariant. Maybe this reference will remind you, but it is not necessary for us. This is just for the expert who knows about homology. So this is another way to define the also for other experts, but for us it may be just a convenient way. You should not know nothing about CW complexes. It is not necessary to do, but if you know, it is, or you can just consider this remark as a economical way to calculate the Euler characteristic. So, Raphael, did you meet somewhere CW complexes?
Yeah, I did.
Okay, very good. So then, for everybody, not for experts, and experts may use me, I just want to give some reference, not examples. Maybe I didn't make it before because they are elementary. So what is the Euler characteristic of the point, right? You have just a point, just a cell of dimension 0, so it is equal to 1. And the same way, it is the Euler characteristic of the interval, right? And the same way, it is, you can either calculate it directly, or you can use, if you consider the Euler characteristic of a disk, consider Euler characteristic of a disk, either you can calculate it by this formula. In disk, you can, if you want to be at the level of polyhedra, then it must be like this. So you have 3 vertices, 3 edges, and 1 2 cell, exactly equal to 1, the alternating sum. Or you can use the, sorry, maybe I, what did I do?
We don't see the screen anymore. We see it back. Yeah, now it's coming back.
I escaped what I wrote, but it is not important. Maybe it's even better. But you can see directly the fact that Euler characteristic is a homotopy invariant. As those subjects which I raised, they were all homotopy equivalent to a point. Then you don't need to consider actually the to consider actual cells in the triangles, right? You can just use this. So let us now look at other. Excuse me, again doing. Excuse me, please. I'm very sorry. I'm clicking the number of the right. So let us consider the circle. Let us at the beginning consider not a disk but only the circle. So what do we see? What do we see? There are 3 vertices and 3 edges. So the Euler characteristic is 0. You see that you can distinguish that this is not trivial object, right? So, for example, we can consider now the tetrahedron, though you can see, but let us look at actually for the convex object like this. Euler first understood, though his proof was not rigorously correct. But anyway, so what do we see? 1, 2, 3, 4. 4 edges. No, 4 vertices. 1, 2, 3. 1, 2, 3. Minus 6 edges, right? And faces. 1, 2, 3, and at the bottom, this is the 4th. So this is 4, and this is equal to 2. Maybe this calculation that
we calculate only Euler characteristic of surface of
right,
surface.
Right, sure.
Yes?
Because for the field, it will be the same as a point. So no, we are we were in debt to the Professor Euler, who made this calculation first, and maybe this calculation, of course, he had done not only for the tetrahedra, but for a lot of for a lot of convex polyhedra, and every time he was having this wonderful number 2, and maybe some people are considering that this calculation was the birth of the topology. Okay, so that we've done for this. So what can we do? Okay, maybe. Okay, I'm again making terrible things. Sorry. Okay, maybe then we look at other examples maybe later, because maybe later a little bit, because there is another wonderful property of the Euler characteristic, that if you have 2 polyhedra and such that the intersection of these 2 polyhedra is again a subpolyhedron, then you can have the following formula. Sorry, I'm again. You can have the following formula for Euler characteristic. What do you remind this formula? What kind of mathematics? Which you are studying in the regular, maybe the second or the third year in the university? This formula. Rafael, you are more close to the regular courses in the university. What you can say about this formula?
Vector space, maybe.
No, very far.
Not this one.
No, not algebra. Look at analysis.
Integration with the measure.
Right, exactly.
This one.
Exactly. But the only essential difference that, and we shall see this now, that Euler characteristic may be negative. Okay, so excuse me. Right. For example, let us make the calculations. So return to CW complex. How to calculate Euler characteristic in more economic ways. So let us consider the sphere. Excuse me. No, why it is always making? I just want to make a picture. To make how it is called. Okay, put it here. Right. So no. Right. So let it be the sphere. Okay. And Natalia, we are considering the surface, only the surface.
Okay.
And we have the following, not necessary for us to consider the polyhedron. Only what is necessary for us is that our decomposition for it should be the cells. So it will be the cell of dimension 2. So one cell of dimension 2 and only one point, which is the boundary of the cell of dimension 2. Dimension 2, this is like this, the disk. And you put the whole boundary to this point. So you can see that if you take a handkerchief and just shrink everything, the circle to this point. So what do you have? You have 1, 0 point, the north pole here. And you have one cell of dimension 2, no cells of dimension 1. So in an economic way, we calculated the Euler characteristic of the sphere equal to 2. So we have the same answer as Leonhard Euler made for us. Okay. So the next. No. Okay. No. Sorry. Anyway, let it be here. Let us consider the following object. Let us consider the age. Okay, maybe sometimes it is written in this way, and people who are not working in the knot theory, they are saying that this is a figure 8. Of course, you know now what is the real figure 8, but this is fake figure 8. Anyway, this is the wage of two circles, wage connected sum in one point. So it's not beautiful connected sum that we are considering, where everything is smooth, but this is just variable with singularity. So what is the early characteristic of this object? You see that this, yes, exactly, very good. This is -1. So this is a remark that we were looking at when we were considering this theorem, which is now okay here, that the Euler characteristic behaves like a measure. If we consider finite, of course, for measures you are always not considering two infinite object. It is sigma finite and so on. But here we are just restricting ourselves to finite object. What can we see? That this is the measure, but the measure which can be negative, which in classical measure theory doesn't, right? So, and now if you consider the wage or bouquet of n, then if you consider this flower, but sometimes in algebraic topology they're saying that this is a bouquet of the circles, then the Euler characteristic of this bouquet is equal +1 minus n. Right. If you consider, if you're generous and you want to give a very, very big bouquet, then you obtain a very big Euler characteristic. So, other questions, remarks? Okay, then we can make further our considerations. It will be helpful for us when we were considering the Seifert surface and so on. So maybe something more about Euler characteristic that so for example, like maybe that is quite another stuff about Euler characteristic that it is not so powerful if we consider the Möbius band. Cannot just write this, the Möbius band. What is the Euler characteristic of the Möbius band? Raphael, what's your opinion?
Should be 0, no?
Yes, absolutely. And why?
So you want to decompose it as we do? Yeah. So we have one cell of dimension 1. We have one cell of dimension 2. Wait. One second.
If you want to do it by cells, let it be. There is this dimension 1, this dimension 1, so 2, and 1 dimension 1 again. This is the same.
This is the same, it's glued, so yeah, here we go.
This is the same. So, and please take 2 points, this one and this one. Okay? So you have 2 points, dimension 0, this is 2, minus 3 intervals, right? 1, 2, 3, and 1 dimension 2. But so I reminded how do you do by the band Möbius. You take the sheet of paper and you just glue these guys with opposite direction, right?
Yeah, you just twist it. Yeah.
Yes. So this will be the 0, and it's okay, but the simplest way, if you just look at the core, I don't know how to say better, the middle line of core of this Möbius band, you see that you can shrink the Möbius band to this.
Yeah, to the cycle.
Yes, to the circle.
It will give a cycle, and we are done.
Exactly, Raphael. So from point of view of homotopy, the Möbius band is a circle. So it's wonderful, but it is so. But if you want to consider it as a manifold, that's what is the simplest way to see that it is not equal to the cylinder, for example. The cylinder, we will look today at the cylinder also, but cylinder, we are considering only the surface, Natalia, the surface of cylinder, and without these points, and without these surfaces, just the cylinder as a product of circle to interval. It is also equivalent to equivalent to circle homotopy, but it is not equivalent to Möbius band. This is orientable, this is not. And for example, the simplest proof is the following. If you are looking at the level of surfaces, the proof is simple, that this surface has a boundary consisting of two circles, and Möbius band has a boundary consisting of one circle. So that's why they are different. But from the point of view, they are not different. So Euler characteristic doesn't give us a good tool to distinguish them. But anyway, we like Euler characteristic. Okay? So, other questions at the moment? But if we want to close the Euler characteristic, to close, sorry, the Möbius band, we should consider the projective plane. In projective plane, maybe this is not if it is if you are not familiar with the stuff that I'm telling, it's no problem. Just a little bit about Euler characteristics. So, what is the projective plane? Projective plane is the number of taking into account all the lines on the straight lines which pass from 0 in R3. This is the, if you take all of them, this will be the projective plane. And so we can identify it as each line, straight line, intersects the sphere, in opposite points. So then it is another economic way to see the projective plane. It is the sphere with opposite points identified. So how can we now calculate the Euler characteristic of projective plane? What are the cells? What are the cells in projective plane? How can we calculate?
We have one cell dimension 2, one cell dimension 1, and one cell dimension 0.
Very good. Exactly. We can see this in the picture. So first of all, we can take away what is, oh, excuse me, it's too, sorry for that. Excuse me. Oh, it's good. Excuse me. So we can take away which is in the south hemisphere, right? We don't consider that the Earth is something in the south hemisphere, as there exist people who don't believe that the Earth is close to the sphere. So we can take this, but it is not enough. We should identify the opposite points. So if we are considering the upper hemisphere, we still need to identify this interval and this interval, and this point and this point. So we exactly have 1 point in dimension 0, 1 age in dimension 1, and 1 age and 1, sorry, phase in dimension 1. So in dimension 2. So Euler characteristic is equal to 1, right? So this is the and do you see what is the connection with this one of the Euler characteristic of projective plane and 0 of our Euler characteristic with Möbius band?
Can you ask again the question, please?
The question is that, can you compare or make any explanation? We were calculating the Euler characteristic of Möbius band. It is 0. We calculated the... Yes.
It's just a sphere. We take out the top of the sphere and we glue a Möbius band to it, according to the boundaries.
Yes, because of the boundary. Very good. Very good. I'm very happy. So, yes. Okay. So now let us move to our surfaces. Okay. Why it is? I want to. Let us move to our surfaces, because we need, actually, this was done in order to make exact calculation of genus of the surface. Actually, the Euler characteristic of closed orientable surface is calculating the following way. It is 2 minus 2g, where g is the genus. So genus is the number of handles. And what is especially interesting for us, because we shall consider the one boundary component. It was exactly what we were doing with glue and scissor. We were calculating not calculating, but constructing, really constructing the work of constructing the Seifert surface and here. So explanation why it is so. If you know, you can add this. So you can to how you construct the standard way to construct the surface. You consider the G gone, right? Consider, let it be A, let it be considered B, and then let it be considered A, and let it be consider B. I'm writing I'm writing a typical part of a surface, that AB, BA. So this is exactly the same as you are considering the torus. A, B, A, B. Right? So, and in general surface, you have G times this. You have G times this. And if you glue according to the arrows, these include this one, this is glue, this one, and then corresponding A2, B2, and so on, just for the AG, BG, you will have the, if you glue, you'll have the picture of genus G, closed picture, everything will be without boundary. So now you can calculate. You'll see that all these points, for example, you have these points starting with A. It is a starting point with A, but this is the final point with B. It is here, but this is final point with A, so it is the same. So you see that all 4 points are the same, actually 1 point. And continuing this, what do we see? Suppose what we see? We see that there is 1 point in dimension 0. Because of identification, AI is either this edge is identified with this edge. So what do we see? We see that there are, corresponding to A's and corresponding to B's, there will be 2 G edges, right? And of course, not forget the surface, because we are actually speaking about surfaces. Right? This is one. Okay. And okay, so what this is the, sorry, this is not this formula, but without this one for this one. So you see that it will be exactly 2 minus 2D. And in particular, you see that you can construct the sphere with G handles. So you have, if you write like handles, you can construct a lot of handles and you get the surface of genus 2000 and so on. And you see that this surface will have very, very negative Euler characteristic. So it is actually in the domain where Euler characteristic is considering a lot. This is surfaces. It is basically the negative object. So how to come to this formula? Now you see this is simple. You just consider surface. You consider circle like this. And what do you have? You have one more H. If you want if you don't like this, you can subdivide it like here, or you may put a triangle. Anyway. And if you don't like this situation, you may consider the circle inside, real circle, and then connect it and calculate this, calculate h this. You will have two more edges, or anything you want. You can have a triangle here, but anyway, you have two more edges and one more extra point. So anyway, you will have this -1 here, right? So this is the formulas for our wonderful surfaces. Other questions, remarks? Natalia?
No.
Very good. So we can move further. So the same way, we don't need it, but just for the completeness of our consideration, I put down the classical thing that the early characteristic of closed non-orientable surface. Non-orientable surface, this is the genus is considered how many Möbius bands you should Möbius strips you should put on the sphere, and this is the formula for Euler characteristic. That's why we have this. If our surface is just a projective plane, you have 2 minus 1. Projective plane is a sphere with glued one Euler or one circle, and we get 1 here. So it's so now we finish. If you have questions, please interrupt me. Then we are coming to our surfaces and knots and genus. So the following thing that we need to understand, that the genus, the only knot with genus equal to 0 is the unknot. Okay, and of course you see that the unknot has genus 0. You can just glue the disk. Disk is genus 0. But what do you, how to do? Maybe it's clear intuitively, but maybe a little bit more consideration. So if you consider a disk, and this is a disk. No, I'll write disk. And you have a boundary. You have, this is in the boundary. This is our knot, right? And this is knot of genus 0. The genus of K is 0 because of this disk. So evidently that we are considering, we are working, if you want, some arguments in this statement, then we are working in PL, piecewise linear category. So actually our disk is a piecewise manifold that is triangulated. Our disk is triangulated. So we can, what does it mean? That we can use these triangles of our triangulation of the disk. We can use them and to use the delta moves that we were looking when we were studying formally the knots. So knot is the polygon, and we consider moves. So we can step by step. No, sorry. Not a good idea. Excuse me, please. So it just when you just touch and all disappear. So it's not necessary that disappear all the triangles, but I want to illustrate at first just one triangle should disappear. But as we're working in PL category, what does it mean? That step by step, all triangles disappear except the one which we can place in the center, any way you want. And here you have exactly the trivial knot. And as we were working by delta moves, each time by definition we were cutting these and these and these and these. Finally we got triangle. And triangle is by definition the triangle without interior points, the just lines of triangle. This is by definition unknot. So by delta moves, we make equivalence of our K to unknot. So this is very simple, but I made these arguments in order to, because this is quite essential for our study of surfaces and genera. Okay, other questions for the moment?
All is okay.
Natalia?
Sorry, my internet is down and I only in this moment with you.
I can repeat if you want.
No. Let's.
So you agree with this statement? Essential for us that the only knot whose genus is 0 is a knot.
Yes, I agree.
So we can go further. If somebody does not agree, tell me, please. We discuss. Okay. So now we return. It's very good because we return to our stuff that we were doing with Seifert surfaces. And Natalia showed us beautiful surfaces. So let us start. We want to calculate that the surfaces that we were constructing actually has the genus 1, and then the trefoil and figure 8 has the genus 1. So if you remember, I can repeat here. If you have your surfaces, you can look at them. So we are following the arrows, right? This big, including what is inside. This is 1. And another Seifert circle is, I'm writing a little bit smaller. So there are 2 discs, right? You remember? And we need to make bends in this. They are crossing bends. Sorry, I'm very, very bad painter. But you remember, this is other bends. So if I make description badly, but you remember what you were doing really, real, not theory. So what is the genus of the surface? Now we can calculate easily. Why the genus? Because it's equal. My question is stupid, but why genus of this surface is 1?
We have one face, we have 2 vertices, and we have 3 edges.
Why 2 vertices? I don't see.
Vertices is a circle. Out circle and inside circle is the vertices.
No, vertices is of zero dimension.
Yes, but this is head graph, ribbon graph, and we have maybe I see dual of your picture in my mind. I see 2 vertices. Big circle is vertices in.
I can see. I can write. I can be painter for you. Two vertices, right?
Yes, and
then
3 edges. Our
3 edges.
3 edges. Yes.
How?
My.
How do you connect these vertices?
3 edges. Each edge is 1.
Like this.
One end in one vertices and 2 end another vertices.
Like this.
Tetragraph. And
yes.
we have 1 faces because if we follow line, we have only 1 big line and 1 face. We put 1 face and we have torus.
Very good, very good. But as for me, this picture is enough. Raphael, do you have a remark from your part?
Can you explain quickly again? I didn't get exactly.
Why? My question is, why this picture is enough for calculating the genus of this Seifert surface? Why the picture that this graph with 2 edges and with 2 vertices and 3 edges is enough?
So, and we have 3 faces then?
No, we have only 2 faces.
And in the
we have
exterior
a big
face.
one. We have a
Yes.
big one. This
Yes.
is the small one. Only
No, but
two
on
faces.
the graph on the right, you have one on the upper one, the down one, and the exterior one. No.
In the graph here, I have two edges.
One faces, two faces, and
No
the
faces.
one outside.
Oh, you're making complicated. Just see the graph. Just
Yes.
see the graph.
No, this is only graph without surface. In surface, this graph like another C in torus.
Yeah.
Oh,
So,
okay.
so remember, please, our remark that Euler characteristic. So actually, we need to calculate the Euler characteristic of this type, right?
Yes.
Because we immediately calculate the genus by the formula 2 minus 2g minus 1, right? So Euler
Yes.
characteristic we need to calculate of this surface. And Euler characteristic is homotopy invariant.
Yes.
So each disk is the same as a point.
Ah, no, okay, yeah, okay. You just okay.
Yeah. Each disk is homotopy equivalent to a point. And each ribbon, as Natalia said, this is a ribbon graph. Each ribbon, no matter how it is twisted, or at the moment we are not interested in this. We only have this graph, 2 vertices, 3 edges. And as we can easily calculate, 2 minus 3 is equal to minus 1.
Yes.
And now 2 minus 3 is equal to minus 1. And remember our formula here. Sorry. This is minus 1. So G is equal to 1, right?
Yes.
This should be minus 1. To kill this 2, you need to be G to be equal to 1. So we didn't have, of course, I'm sure that Natalia knows that the surface that we were looking and we were constructing was the genus 1, but we didn't know the exact calculation. Now with Euler characteristic we can do this easily. So again,
I calculate like you, 2 vertices and 3 edges. And
right.
For our construction we have line in our node. And this line, this circle, is one face in my surface. Yes?
Yes.
And we have a genus 1.
Yes.
Okay, like you.
Very good. Very good. So now let us do the same thing for our favorite. You can now do this easily, right? Sorry for that. You can do now easily. Excuse me. You can do now easily. Construct Seifert surface. This one, I'm unfortunately, here we need to do this, right? This is our first disk. Here is our second disk. And here is our small third disk. So we have 3 disks. And we have, I write schematically, as this is figure 8 is 4-1, so it has, by definition, it has 4 ribbons, right? So the same picture as before, each disk is a point. But here we now have 3 disks. A big one and 2 small ones. And there are, say, let it be, for example, this one be big, this is small, then again this one, and a big one is connected with 2 ribbons with another one. So this is a big one, and these are 2 small, right? We have, but essential here is that we have 3 points. This means that we have 3 disks, but they are homotopy equivalent to points. And we have 3 ribbons, which are equivalent to 4 edges. So what do we have? We have again -1. So we see that the Seifert surface that was constructed directly by paper, glue, and scissor, we have that it was actually torus with 1 knot as a boundary component, right? So, what are the questions? So this is about our early characteristic, and we found wonderful if we now apply the theorem, which we didn't prove yet, but we know the statement that the genus of a knot is additive characteristic of a knot. So what can we conclude? We conclude that figure 8 and trefoil, they are prime knots because they cannot be decomposed. If they could be decomposed, then you should decompose 1 in the integer numbers, but it is not possible. So the corollary from the statement is that figure 8 and trefoil are prime knots in decomposition. And so we come to the proof, and the proof is geometric, and so it needs some concentration and considering circles, disks, and so on. So if you don't mind, let us have a break, 15 minutes. Okay?
Okay.
Okay. Да уже тут...
Shall we continue?
Yes.
Okay. So the principle, one of the principal theorem in the knot theory is the theorem of prime decomposition, and another important is the theorem on genus. I can remind this beautiful theorem that we were approaching. This is the genus of the product. Connected sum is just a sum of genera of the knots. And okay, so let us start. There is, of course, the simple part and difficult part. Suppose there are knots K and L, and there are surfaces with minimal number. So there is surface SK and surface SL, such that the genus of each surface is exactly the genus of our knot. This means that minimal of all genera possible. Of course, just to remind, if we consider in any disk that you have in your surface, you can attach a handle. So to make the genus bigger, no problem. The problem is to find the minimal genus, the surface. So suppose that they are exactly such surfaces that they give our genus. So let us glue them. So you have, say, let it be this one guy. This will be K, and this is his Seifert surface. This is L, and this is the Seifert surface of L. So what do we do? I'm sorry. We cut our surface in the same way. This is part of a knot. We cut it by this part, and then, if you remind, everything is oriented. Then we construct the connected sum of K and L, and we glue a band or ribbon, as Natalia would say. So this is also oriented ribbon. So we get a surface. We get a surface. And you see that the genus of this surface is exactly equal to the genus of K plus genus of L. We can see. So what do we have? But it doesn't mean that this is a minimum. This is just a surface. This is just a surface with some genus, but maybe there exists another surface, not our, just constructed by force directly. Maybe exists another surface, for which the genus will be smaller. So in general, we have the following thing, and we have proved that. If we continue now, I didn't wrote this, but it's evident that we proved that the genus of K plus genus of L is greater than genus of the connected sum. This is simple. Okay, so actually we want to prove that it is exactly equal. So let us now take the surface, another surface in general, that not constructed in this way, but the surface that the boundary of this surface is exactly the composition of K and L. Take this surface and try to understand its genus. So what should we do? Look right. So now we can forget about the surface S, but let there be our not K plus L, K composition of L. And this is in space like this. There exists a plane P such that in one half plane we have L, in another half plane we have K. But at the moment there is no surface S, just this one. And now delete this surface which is gray here. Please delete it and put any other surface. Not any other, sorry, a bad word. Put a minimizing surface in this setting. So you have knots, you have plane, and you have another surface, minimizing surface, which the problem, what is the problem with this surface? The problem is that it is not it is not placed in such a wonderful way that some part of it is lying here and gives the boundary K. Another part is here, giving the boundary L, and it is intersecting by the plane P by this wonderful interval. It may be placed arbitrary in the space. It may behave arbitrary. The only problem is, the only statement is that not only, but one of the statements is that the boundary of our minimizing surface is K plus L, and that this surface is minimizing surface, right? So it may intersect, this is our plane, this is our nodes that maybe in this line AB they were here, but the surface behaves arbitrary in the space. Our first move is to place this surface in general position with our plane P. So in general, the set of intersecting surface and plane may be quite difficult to understand, but there is a notion of transversality in topology. In our context, it means that, and this transversality means that the transversal positions, they are dense in the set of all positions. So if you have your arbitrary intersection of the plane P and surface, let it be S, new S, this is another S, be arbitrary, but you can just make epsilon movement of your surface, and it will make a transversal intersection with our plane. Surface and intersection make a transversal intersection. So what does it mean? It means that it will be, this is part A and B, this is the line where we're gluing, so our this is point how to say better, that this is, say, point A, this is point B, so it is interval in the intersection of this surface. So actually this is the knot is here, this is not here, and this is the point of intersection our surface with plane. As you notice, our knots, as they were lying like this, they all out of this plane. So when we are considering these knots, they are out. So the knots are not in this plane. They, by our construction, L is somewhere here, K is somewhere here, but the surface may intersect. So we see that the intersection is this line AB, and several circles. The only what I didn't see drawn here is the following, that it may happen the following unpleasant thing, that a circle may be like this also. Circles may be like this. Okay? So this is the intersection of S and P. So what do? We look at our circles, and you see that it is possible that there should be lonely circles and nested circles. We are considering our work with the smallest circle among the nested. You consider the, say, the several nested circles and take the smallest one. Look at the situation, what it will be with this circle. What it may be. So, no, I didn't draw another picture. So I tried to explain by words. So what should be, what may be there. The idea when you are considering this circle, you should notice that the only possibility is that there is a cap here. There is a cap. Sorry, my cap is very bad. I try to do better cap. No. Should be only the cap. That it is not possible that our plane, which is here, I just like, no, it's bad. That our smallest circle would not cut the tube. Suppose that this is this smallest circle, and it cannot cut the tube, because if this happens, what can you do? you can change your surface. If there was like this, our tube, no, it's bad. No, it's. So why it cannot be that it is like a cylinder or a handle that is cut? What can you do? You can take, this is this tube, but you can cut this tube and put in these places 2 discs. This is evident. This is evident that you can evident by intuition that you are cutting the handle, or you can do this by calculating Euler characteristic, what is happening when you are gluing these discs. This will mean that the resulting, so okay, sorry, I need to be more precise, excuse me. So when you cut this surface, you see that the knot, now you have 2, maybe not components, but if you have that it belong the same component, it means that the genus, you calculating the Euler characteristic, that the genus of this surface will be smaller than that one. The only possibility is like this, that you may have something like here, that it goes, then goes this way, then this way, then a small cap. But when you cut over here, this will be nothing but cap. Because if this will be more complicated, then the genus will be, after cutting of this part, of one part, will be smaller. So the only possibility is the following, that when you have this surface, you cut by this small disc, and you threw away this component which is disconnected. Connected it could not be, because as I told you, the genus of resulting surface will be smaller. Then you can take away this this part, because this is nothing but not necessary cap which is attached here. So I'll see maybe the previous picture. So, okay. So, right. So in this picture, I need to erase. I need to erase. So look at the situation. Here you have exactly 2 circles and the small one. And this shows the idea that, for example, here, if you cut here, you will have a surface with smaller genus. You cut here, you took two discs, and the Euler characteristic show you that this has the smaller. So this situation is impossible because our supposition is that S is of smaller genus. So the only possible, but it is quite badly seen here, that a small has a small cap, but you can cut here and throw away this part. This will be the small cap. What will be rest? It will be this cap, which at this part. And the same way now you should take away. You should take away. So starting with and now starting with this, then we starting with a small one, we killed all the nested, and then we tried to kill all the unnested circles, and all these circles disappear. The only circle that is not drawn here is that one, the 2 stars like this, which go around. So how to deal with these guys? Here we need to deal contrary to deal with the biggest one. We need to deal with the biggest one and to see what will happen if we glue say in order to avoid, you can not consider the cutting like this, but you consider a disc glued like this, where our knot is somewhere here. So you are gluing this one, this disc, and the same way gluing these discs, we can erase this one and then a smaller one and so on. So this is the procedure that we can, so, and by gluing this we see, and then we can move, for example, this disc and the disc glued, you can move a little bit so that you can take away this big circle. Then you probably in this direction or in another direction, you can take away this circle. And this finally means that in our excuse me. in our transversal intersection of the surface S, there are no disks, no circles. So what does it mean? It means that our surface, these guys, also know the big guys. Our surface intersects the plane P only by this line. So if, for example, here, before you and before me, on this part, there is K, and here, from that part, there, which invisible, is L, and our surface does not intersect the plane P. What does it really mean? It really means that our surface behaves not like this, but it is completely divided by our plane P in two parts, which can we baptize as SK prime, SL prime, doesn't matter. But essential is that each SK prime.
Sorry. We prove that if we have one surface and second surface and sum of this surface genus of our sum is sum of genus. Yes.
Yes. Yes, but not finished yet. It's a little bit consideration that
for our realization, for
right.
our projection, we have one projection of our first knot and second knot, and we glue together, and we have projection, and we calculate projection genus of projection of sum. Yes.
Right. Right. And then yes, but and another remark.
We sorry,
Yeah.
I don't understand. We prove for any two surfaces. This picture about we have two surfaces and glue together two several surfaces. This surface not about our knot. Yes?
No. Okay. Sorry, this was our first consideration. This is our first consideration.
Okay, this picture is right. But
right. But now, okay, let the starting point. So with this picture, we proved this one, that the genus of S is greater than genus of K plus L. This is what we proved.
But how? I don't understand, because I see the picture in my mind, and this is equal. I don't understand how large. surface.
This is very good because this is the simplest part. So this is K, or if you need projection, this is a plane which looks for you. This is a plane. This is the projection of L, and maybe not projection. Let it be K. Let it be in surface, in space.
Any space, not
No.
for not. It is
No.
a difficult theorem, but for our to not is very simple. But maybe I don't understand what happened.
No. You understand perfectly well. So let it be R3, our space. Let it be R3. Okay.
If we have two surfaces and or one big surface in R3, and we cut plane our surfaces, this is a very difficult theorem that one part or two part. But if we have only not surfaces with one face and glue little line in face to face, this is a very simple.
Right.
Maybe I don't understand what happened, and
no, it's very good. So the first part. Remind everything happens now in R3. In R3. You took in R3, you took two knots. You cut them by this line and you glued by two lines, two intervals, them oriented.
yes, and let's calculate our Euler characteristic, and we have equal.
No. Look, but
I see your picture, but I don't understand why we cannot calculate Euler characteristic for our picture.
yes, we can, and we are doing this, and we are obtaining inequality. Look, this is the not K, this is not L. We construct for each minimal, as K is minimal, so it has minimal genus, not arbitrary, but minimal genus for K. This has the minimal genus for L. We just glue them together, and exactly, you are right, we are calculating that the genus of this glued surface is exactly G of K plus G of L.
Yes, okay.
But remind the definition of genus. The genus of a knot is a genus of minimal surface. For this, it's okay. But maybe it exists another surface, not obtained by this procedure, but another, taking, maybe your friend will give you another example and will give you another surface.
If we have one knot, we can have more genus. Yes.
Right. For example, Natalia, look. Take this here, and just glue a handle. And you'll calculate Euler characteristic, and you'll get that the genus of this guy is here plus 1. Okay? So you have, this is a general logic that you gave an example. An example only shows
Sorry,
you
if
inequality.
we Ordemeister move, genus is not equal. Yes, I think if we Ordemeister move, genus is equal. No.
No. Look. Ordemeister moves concerns the knot, and I especially took 2 discs in your surface and glued a handle.
This surface, but no, this we cannot glue this thing, because in our construction we have ribbon graph with 1 faces, and in our faces is in our surface is not Короче, мы не можем приклеить туда вот эту штуку так безболезненно, потому что у вас именно вот такой граф, который, когда вы вырезаете, остается один многоугольник по вашей конструкции, и никаких таких штук там нет.
Yes, but look, the definition of genus is not a genus of what we constructed, but the definition of genus is the genus of minimal surface. The genus of a knot is a minimal genus of a surface, not a genus of construction.
But if we have a ribbon graph or descent on fan in our construction, we have descent on fan. It is a minimal genus. It's okay. It's your construction is very good, and this is a minimal genus.
I think this construction were known long before I was born. Anyway, this is the definition, but you rose very interesting question, why the genus is defined. Look, Natalia, I have an argument. I have an argument for you. This construction and your graphs, they depend on knot diagram.
Yes.
Knot diagram. And for example, I can, or somebody can give you the trefoil with
let us example. Okay, trefoiled. Let us.
Yes, and suppose
for trefoiled another not tor. Okay.
Yes.
Let's see.
And if you I didn't check, but it is, I think, worth to check. For example, if you have trefoil, which gives you the 2 bridge, I suppose that you will have another surface with, or I can conjecture, but I can check you for the next time. So if the
I think only genus is equal for every projection, I think.
Okay.
Maybe I don't understand, but I think, okay, I think.
Are you sure? Okay, but
I don't sure, but
for example,
вот давайте для просто узла, для незавязанного посмотрим. Для незавязанного узла, как вы там не изощряйтесь, у вас все равно получится дерево какое-нибудь на... Нет, не
Хорошо,
обязательно
а
дерево, но у
если...
вас получится всегда планарная штука такая. Ну,
And
которая на срезе.
if I take just a usual torus and just cut a disc in torus.
Yes, but your construction, you cannot this picture.
Okay.
This is not ribbon graph. Ribbon graph, if you cut in your vertices and edges, we have only one faces, but not tube in your construction. It's okay?
Yes, I agree with your arguments, and I don't have example. The only
okay, I want example, but I cannot understand.
Yes, but the only thing I can say as an argument, of course, it's stupid, but the following thing that the people who were defining genus to be the genus of minimal surface.
Yes, but your construction, give you minimal surface. Surface minimal genus. Your construction. We can can put your not on surface highest genus, but this is if this construction give minimal surface.
That's true.
Surface.
That's true.
I think that's true, but
yeah, this is true by the theorem, because we prove this one, but we need all these considerations that I was trying to present. Of course, it's because the formula it actually means that this surface is minimal.
No, construction of your ribbon graph. And if we glue together the two surfaces, we have a ribbon graph. Your construction sum and construction, your ribbon graph is very good, one-to-one, and we have minimal surface. Sorry, my English is very bad. I cannot say my mind.
It's okay. It's okay, but anyway, I'll check for other projection, and I can't say it immediately. So, but it's interesting. I understood your remark, and unfortunately, I can't immediately give a response that for example, to make some maybe specific diagrams that will give another genus. Maybe I suppose it exists. Okay, but anyway, let's continue. Okay, I'm listening. Okay, sorry.
For very interesting for me. What genus? What happened for our ribbon graph or descent and fun if we have the master move? For it's very interesting, and I think if we understand for the master move what happened for our ribbon graph or descendant fun, we can understand we understand what happened for our surface, and we understand what happened for our genus.
Yes, but for graphs that I remember, I can tell you, So what is happening with Reidemeister moves? One of the moves, maybe the third one, is the following: that if you have the graph that we constructed for our checkerboard, then this Reidemeister move corresponds to this one.
No,
There is
this
the following change. I don't remember by heart, but something like this. In the graphs that we constructed, there is the following change of structure. If
okay,
you have,
but if we have this moving, we cannot change our genus. Yes.
Yes,
Okay.
yes, you're right.
Sorry, I think about it. Maybe. Может быть, мне нужно больше подумать. То есть я, может быть, не совсем понимаю, что происходит. Но мне кажется, что все, что вы делаете с этими трубками, это просто лишнее, потому что ваша конструкция он никогда не получится.
Maybe.
Извините, пожалуйста.
No, it's okay. I'm very, but here the early characteristic is changing. Here we have 0, and here we have 1.
No, this is a small part of your big graph. But if we have graph on sources, we cut triangle, but glue to this part. Извините, короче, мне самой нужно подумать об этом побольше. Я сейчас не могу.
We shall. No. It's quite. I'm very happy that there is so vivid discussion, and we can even continue next time. But suppose anyway, we have not many time, but I think it's time to finish, because to finalize, I have 10 minutes, if you don't mind. So do I have 10 minutes, dear friends?
Yeah, sure.
Okay. So anyway, the problem that Natalia raised is very important, that the connection between Reidemeister move and Seifert surfaces that we constructed. We have opposite opinion on this subject, so it will be interesting to verify. Maybe everybody can also look. The problem is the following: I can formulate it with as an exercise, but I can just tell you. The problem is the following: that we are constructing the Seifert surface according to our concrete diagram. For example, look here. We take a diagram and we construct disks, and we calculate the genus. I suppose that the genus becomes 1 because we are very lucky to find these beautiful diagrams. And if you take ugly diagram, then the genus may change. This is my opinion. I didn't check. And Natalia says that the Reidemeister move does not change the structure and the genus. So we can consider it as the exercise number 1. But anyway, let us continue, because from the part of Natalia there is no objection to the statement of the theorem. So, but we shall discuss again this theorem next time. But I just want to have have the results of this theorem, because it's very important, and I think it will be answer for one of the questions that Raphael made previous time. So the theorem of the unique prime decomposition. So the statement is the following. Each non-trivial knot is a finite product of prime knots. And these factors are uniquely determined up to permutations, of course, because it is commutative structure. So, so look, what does it mean? For any knot K, you can make the following decomposition, where each Ki is a prime knot. And suppose now you have two decompositions. Then N is equal to K, N is equal to M, and Ki or Kj, Kj prime is equal, or Ki prime is equal to one of these guys. only what is allowed, this is permutation. But permutation is in the nature of this operation because it is commutative. So other questions for the main theorem for today? I mean for the statement. The proof of this part is very simple. It's very simple. So it is the following. It is the following. Look, it is like for numbers. So look at the knot K. If it is prime, then we are okay. We obtained this, no problem. But if a knot K is a composition knot, it is a product of K1 and K2. What can we state? We can state, look at the genus of K. You see that this is genus of K1 plus genus of K2. And we know that each of them is bigger than 0 because we prove the statement that only a knot is of genus 0. So it means that G of K1 is strictly less than genus of K. Genus of K2 is strictly less of genus of K. And we have done. So it means that the process of decomposition, could not continue to infinity. You will obtain a knot which is not decomposable. For example, you obtain what you have, the knot of genus 1. You cannot. You see that as a corollary. Maybe I didn't state it, but it's evident that every knot of genus 1 is prime. So it means that for any knot, you can finally find an atoms, which, like Greeks, consider that atoms are not divisible. So you can find them. This is the simplest part of the theorem, and this part is difficult and complicated. I mean that nothing difficult in the sense that it is in the spirit of our consideration, which were criticized by Natalia, that again you are, but not only surfaces, but you consider your knot, and it should like in its own either half space or a small sphere, and considerations like this, but even you should be even much more concentrated and much more complicated in the same spirit. Nothing complicated in the sense of mathematically, but considerations like this. So as in many books, it is not proof. They are not given the detailed proofs, but just saying either there are articles which still make the proofs of this theorem. So I will skip the theorem. The proof of the second part. The only thing I would say that it means that this theorem, Raphael, are you with us?
Yes.
Do you see, and this may be, I didn't formulate it, maybe I should write down. You see that this theorem gives an answer to your question about the structure of the semigroup and the structure of the corresponding group if you make the localizations. That means that if you like for, you see?
Yes, I do.
The only thing what is necessary, we shall prove soon, but we don't know. If you add the following thing, that the number of prime knots is infinite, but of course it is countable, as the number of crossing is countable. So the number of prime knots is countable, right? So what does it mean? That you may now construct the one-to-one correspondence bijections between prime numbers and prime knots. Right?
Yes.
And this part of theorem is saying that your semigroup of knots is exactly the same isomorphic to the semigroup of positive integers with respect to multiplication. Right?
Addition.
No, multiplication.
No, multiplication, yes.
Because it is semigroup. It is semigroup. So you simply, for example, you make the following map, application, bijection. Two, you make, for example, anything will be okay, but trefoil. 3, the left trefoil. 5, to figure 8 now.
Yes.
and so on. And the same way that you have prime decomposition of numbers, you have prime decomposition of nodes. So the multiple ligative groups of natural numbers not in the French sense, which starts with 0, but which starts with n. So I make like bigger than 0. Or sometimes in France they are noting like this, okay?
Yes.
1, 2, 3, and so on. This is exactly the same semigroup of nodes. Because you have, because of this part of the theorem. This is because of this part of this theorem that any number you can decompose in prime numbers and uniquely. Okay.
Indeed.
So that's all what I want to say for today. Thank you for attention.
Thank you. Thank you very much.